Okay, so one of your assignments with Geologic Time is to complete the Geologic Time lab. Like with all the other labs, I'm going to give you a handout that explains some of those really important principles that you'll use in the lab. Things like superposition and original horizontality and all of Steno's principles and Lyell's principles. You'll have all of those in this explanation, in this handout. It'll go over unconformities, a little bit about fossils, and a bit about radiometric dating as well. So let me then show you some of the activities that you will be doing in this. So for example, in these first activities, you'll be thinking about relative dating. For example, right here it says using relative dating principles, answer questions 1 and 2. And so this question number 1, in figure 7, which is older, the granite or the sandstone? You have to start thinking, well, what principles could I use to answer this? And in this case, if you look carefully, there are pieces of the granite inside the sandstone. And remember, that is the principle of inclusions. So now, using that principle, you can figure out which one is older. And that's what some of these first activities are going to be, using principles like that. Now, on this next page right here, you have what's called a cross-section, a side view of the planet. And there's all kinds of different rocks in there. So if we look at this, it says list the rocks in the correct order of formation based on relative dating principles. The rocks labeled granite and dike are intrusive igneous rocks. The rock formation labeled A is metamorphic. And you have to put these in order. And you'll see right here on the side of the lab, we have the oldest down here, the youngest here. And so you will figure out what age they are. And so you might say, well, the dike came first, and then rock A came, and then rock D came, and list them all the way to the youngest. Those, of course, weren't the right answers. But just remember, in geology, we always list oldest at the bottom and youngest towards the top, because remember, that's the principle of superposition. So that's what you'll be doing here. Now you'll also see in this cross section we have this line, this darker line, x to x prime and y to y prime. Those are unconformities. And for questions 4 and 5, you will have to figure out what kind of unconformity those are. You will also have a little bit more complex one of these cross sections right here. Now in this one, you are not just figuring out the order that the rocks went in, but you have to also add in when things like unconformities, right? This dark line here that's labeled O, that's an unconformity. This line right here, labeled H, is a fault. You have to add those in as well. And again, we have from oldest on the bottom to youngest here. Now, just to kind of clarify some things, you are also given a key that shows you the different rock types. So if you're wondering if something is igneous or metamorphic, you can come down here to the key and use that to help you when you're looking at those. In Geologic Time, you will also be looking at fossils. And for question 9, you are going to look at a geologic time scale that is provided here that has the different time periods, and it tells you when different organisms were alive. That's these little black lines next to it. And some questions will be referring to asking you which fossils are older or younger or what time periods they come from. Now, a little more complex than that is this bottom part of the page, where you are going to identify the fossils that are shown. And you might be saying, how the heck am I going to do that? Well, I give you a page or two where there are different fossils listed. So you basically have to match the fossils with the on the identification chart here. And for example, this fossil here, there's the name, Annularia, and then underneath it, it says it existed from the Devonian to the Triassic. So that's when that particular species was alive. So on this part of your lab, you're going to look at each one of these fossils, identify what it is. Now in the next part of the lab, you're given a chart like this. These are your different time periods. There's the fossils that you identified. So for example, let's say fossil number 1 was Annularia. It's not, but let's say it was. And we just said that that species existed from the Devonian to, what was it, the Pennsylvanian? So we're going to mark in, it existed in those time periods. So if we find a rock that has Annularia in it, we know it must date to these time periods. Well, what if that rock also had another fossil in it that existed from the Mississippian all the way to the Triassic? Well, let's shade this in. So what that tells us, if the rock has a fossil that existed from the Devonian to the Pennsylvanian and one that existed from the Mississippian to the Triassic, the rock must be from one of these two time periods because that's the only time when those fossils coexisted. And that's what you're using this chart for. You're going to identify these 6 different fossils, tell me when they lived, and then figure out a rock that had all 6 of those fossils in it, what time period could it be from? And that's what you're going to be doing there. All right. And now, you're also going to practice correlation. We talked about correlation was where we're trying to figure out which rock units are equal to each other, right? Which ones formed at the same time. And this paragraph tells you a little bit about how correlation is done. We discussed it in lecture, where it can be done looking at the rock type, the color of the rock, the fossil composition, a marker bed, something like that. So we have quite a bit of information here, and then one of the things you are going to do is you are going to take these stratigraphic sections and correlate which rocks are equal to each other. And for example, you might say, okay, let's start between section 1 and section 2 and see which ones we think might be the same. Well, if we have cross-bedded sand here and cross-bedded sand here, we might say, all right, these 2 rocks should be equivalent to each other. We might then look here and say, all right, we have a fossil in here that's the same as a fossil in here, so these 2 rocks are equal to each other. And that's how we're correlating these together. And then you will go from section 2 to section 3 and do the same thing. And then eventually you'll have worked your way across the whole area, telling me which rocks are equal to each other based on rock type, bedding type, fossil composition, and so on. All right, now last but not least, we come to the radioactive decay part, the part where you have to do math. And that, of course, is going to sound challenging, but it's actually not as bad as you might think it is. And so, in any case, radioactive decay allows geologists to determine the numerical age for rocks. Figure 16 shows the radioactive decay curve, some common isotopes, and half-lives that are used to figure out this radioactive decay. So let's do number 15 together. You would like to know the numerical age of a basalt flow, a type of lava flow. You send several samples away and you end up finding out, let's see, they're going to use the uranium-235 lead-207 parent-daughter pair. And the analysis shows that we have 71% of the atoms are the parent and 29% are the daughter. Let's figure out the age from that. So here's our radiometric decay curve. And then if we look down here, these are decay parameters. Here is the percent of the parent atoms. There's the percent of the daughter atoms. That's how many half-lives went by, and this is how to calculate the age. So if we have 71% of the parent atoms left, we look down here and we say, hey, look, right there, there's 71%. I round it up, right? 70.7 is good enough. It's 71%. So we come across here, and it tells us to calculate the age, we take 0.5 times the half-life. Okay, that's nice. But what's the half-life? Well, you find out the half-life up here on this chart. We said that the parent-daughter pair used was uranium-235, lead-207. And the half-life of that is listed in this column. The half-life is 713 million years. So what you would do then, you found out that the equation is going to be 0. I'm doing fives. I have to write upside down. 0.5 times the half-life, which was 713 million years. So 0.5 times 713 is what? Something like 356.5, maybe? Hopefully someone out there has a calculator, because I just did that in my head and I'm not sure if I did it right. Yes. All right, my husband to the rescue. He just told me I did it right. So in any case, that's how you figure out the age of the rocks using your isotopes. Now, the next question is going to be a little bit more in depth, because we're not giving you the percentage. You have to calculate the percentage, right? You're going to be given 1,071 parent atoms and 7,497 daughter atoms. You figure out what percentage you have and then do the same thing. Go down here, figure out the percent of the parent, figure out what you have to multiply things by, and make sure you pay attention to what parent-daughter pair you have and what half-life number you should use. Of course, if you have questions about this or concerns about this or something is confusing, you know you can contact me. I'm always happy to help you.